So what if the window or plate that we're thinking about total force on isn't rectangular? Pretend I drew a nice neat circle here, and pretend the top of it is 10 meters underwater, and then it's 10 meters from this point to the middle and from another 10 from there to there. This is probably bigger than any glass plate you would actually put underwater, but just to make the numbers nice, we'll use this. You can scale them to a more appropriate application if you become an aquarium engineer. So we want to compute the total force. We're going to need to slice things up. So a big question is, what's a good way to slice things? So when I've done this in previous classes, someone suggested slicing it like a pizza or a pie. Someone else suggested slicing it this way. Someone else suggested slicing it that way. And what's another good way to slice it? Horizontally. So this one is actually how you might do things in Calc 3, which is a lot of fun, but maybe not what we want to do right now. Remember, why are we slicing this? We want to deal with regions where the pressure is the same across, or for the entire region, and pressure varies with depth. So we want no variation with depth on our slices. So this one is the one we want because each slice is at a constant depth, so it has a constant pressure on it. So now we need to think about what is the pressure on a particular slice and what's the force on a particular slice. So remember, the force is equal to the pressure times the area. Pressure is rho times g times depth. But the area of a slice is now the interesting part. These slices down here, they all have this, all the slices here have the same thickness, but these slices down here are not very wide, so they don't have a bunch of area. The slices up here, same thing. The slices in the middle are wider, so they have a bigger area. So let's kind of zoom in on that and think about if I have a particular height away from the center there, not all the way down to the bottom, what is the width of the window at that height? So we might kind of draw our slice here, and we want to know what's that width. So if I tell you that I'm like 2 meters down from the center of the window, how far over does the width go from the center line out here? Well, it helps to think here about the radius of the window. What would you say the radius is? Looks like 10 centimeters or 10 meters. And now that I've drawn that, I can think, oh, hey, here is a right triangle. So I can say r squared equals height squared plus width squared. If you tell me the height, I want to figure out the width. So let me solve this for width. I get width equals root r squared minus h squared. So if you tell me the height in terms of distance from the center, then I can tell you the width, and then that will tell me the area. So let's think about coordinates here. Before we said here's y equals 0 at the water, at the top of the water, and then this would be y equals 10, y equals 20, y equals 30. And that's fine. Let's think about it in terms of height away from the center. Well, here I'm right at the center, so I could say the height is 0. We could have the heights go up when we move up toward the top of the water or down. I kind of like the idea that the lower we go, the more the pressure, so let's count it as a positive. So we could say this is 10 meters, up here is negative 10 meters, and up here is negative 20 meters. So this isn't mathematically the only way to do it, but it kind of makes things work out nicely. So what's the area of a slice? Well, it's the width times dy, rho times g times, now what's the height? So this d is going to turn into, if I tell you a height of 0, how far is that below the water? It's 20 meters. If I tell you a height of -10, how far is that below the top of the water? It's 10 meters. So I need some expression here involving height that tells me the depth. So take a sec to think about that. Would you agree that height plus 20, height away from the center at plus 20 is the depth? So if I'm at 10 height, then I'm at 30 meters depth. If I'm at -10 meters height, then I'm at 10 meters depth, like -10 plus 20 is +10. And then the width is root r squared minus h squared dy. So that's the force on any particular slice. So add that all up. So that's the force on a slice. So my total is the integral of rho times g times h plus 20 times root r squared minus h squared dy. Is that good? And where do I start and where do I stop? Oh, sorry, not dy, but dh, right? My main variable of integration is h. Where do I start and stop? Well, I might start at -10 meters and stop at 10 meters. So anything I'm missing here? Well, this width was from the center line to the right, but I also have force applying to the area over here too. So I'm going to put a times 2 here for left-right symmetry. Do I need a 2 for up-down symmetry? I mean, the bottom here is symmetric with the top for the shape of the window, right? But the pressure down here is larger than the pressure up there. It's not symmetric from top to bottom. So there's no top-bottom symmetry to use. The pressure is different. Okay, so we've got an integral there. Is that going to be a pleasant integral? Probably not. Maybe u substitution would do the trick, because I have an h squared in here and an h out there, at least for part of it. When we do the plus 20, I don't have an h out there, and we'd actually need something more advanced, maybe a trig substitution or something. So if you haven't seen those, don't worry about it yet. But the main goal of this chapter is to write the integral, not do the integral. One thing we haven't talked about is upper bounds and lower bounds. So what would be a good lower bound on the total force here? Well, probably 0. It would be hard to have a negative pressure here. So we're kind of imagining here that there's water on one side and just plain air or something on the other side. So we're imagining this getting kind of pushed toward us or pushed away from us, not water on both sides. Then the material itself, the glass itself, would be kind of squeezed, but it wouldn't be overall trying to move one way or the other. So 0 would be a quick one. A better lower bound would be, well, remember, force is pressure times area, and we said, boy, if the pressure was all the same, that would make life easy. I could just multiply by the area. Well, we could say the pressure is not all the same on this shape, but we could say the pressure is always greater than the pressure is right here. If we pretended the pressure right here was the pressure everywhere, then the pressure would be constant. I mean, it wouldn't really be what, but we'd be pretending it is. So we could say the better lower bound would be the total area times the pressure at the smallest depth. And an upper bound, based on that idea, would be the total area times what? The pressure at the largest depth, the highest of all the pressures we see. And then you could guess, maybe split the difference, average the two. All right, so that does it for pressure on plates.